All right, so the first thing on your desk should be your lab. So let's talk about this lab right quick. You know what is supposed to be included in a lab report, and I know that you have the sheets, and it does not make sense for you to have to do the lab report when you have the sheets in front of you. Okay, let me tell you what they make you do in college. In college, you buy the lab notebook that has all the labs in it, and then they make you buy another lab notebook just to copy the labs that you already bought and purchased into the other one to turn in. Okay, so it makes no sense. That's my whole point, and you have to pay money to do it on top of it. So you do have to copy this into your lab notebook. Now copy it word for word. Please do not. Don't waste your time, my time. I'm not going to read it that closely. Let's just be honest. So if you waste time copying it word for word, that is your time. But you should copy enough of it that if something happened to this sheet of paper, you would be able to do the lab based off of what is written in your lab notebook. Does that make sense? Okay, so make sure that you get that in there. Your pre-lab questions are included. So make sure this is homework. Those pre-lab questions have to be answered before you walk in the lab tomorrow. And I've already previewed them. They are easy pre-lab questions, and you should be able to answer them. Yes, ma'am? In your lab notebook. Everything needs to go in your lab notebook. And then you also need to copy this data table that is on your lab notebook. This is going to be with your lab work. There is another big data table and another big graph that goes with this. I'm going to make you copies of those, and you can use those in the lab and just tape them in your notebook because, I mean, we don't want to get too extreme with this, and you only have an hour and a half tomorrow to finish 2 titrations, okay? So the graphs I will give to you, but I want us to leave today with a good understanding of how the lab is going to work tomorrow, so hopefully we can get both titrations done. That's my goal, okay? So the notes are going to help. I'm going to be flip-flopping back and forth. Just stay with me. It will work. It will be fine, okay? We'll be able to get this. So what do you need included? You need the title, you need the date, you need the purpose, you need the procedure, you need the pre-lab questions, and you need the data table copied. You should have that in that lab handout, that sheet I gave you. Remember that handout that says what to be included in a lab report? If you don't have it anymore, find somebody that does have it and take a picture, or come see me 7th period and I will make you a copy of it. I just don't have time to make you a copy right now. Okay? So, I'll say it again. You need a date, a title, a purpose, a procedure, your pre-lab questions answered, and your data table copied. So those are the 6 things that I'm expecting from you when you walk through the door tomorrow, and while you are doing the lab, I will be checking for that. That's going to be 1 grade. You're going to have a pre-lab grade, and then when we do the lab tomorrow and you do the graph and you answer the post-lab questions, that's going to be your post-lab grade because some of you need a grade booster, okay? So that's the goal of this, is to be a grade booster, right? And we can handle that? Yes? We're good?
So we don't copy post-lab questions?
So you don't have to copy post-lab questions. We'll answer those after you do the lab. Now that will probably be homework over the weekend, is to get your post-lab questions done. Okay? All right. So on to your notes so we can talk about what is a titration. Okay? Now, if you had me last year, then you've already done a titration. We did it last year. We did a strong acid with a strong base, and we're going to start with that same titration tomorrow, okay? We're going to start with NaOH and HCl. NaOH is a what? NaOH is a strong base, and HCl is a strong acid, okay? So therefore, strong base plus strong acid. I'm going to go to page 4. Sorry, I told y'all I was going to skip around. I'm going to go to page 4. So strong base plus strong acid. So at the equivalence point, my pH should be what? 7, right? Because when I have an equal number of moles of acid and an equal number of base, if they're both strong, then they should just do what to each other? Cancel each other out, right? And so then I should get a neutral solution, which should be 7. The first question on your pre-lab questions is going to ask you to write an equation of what happens here. So I take HCl. I put it in NaOH. What do I get? First of all, this is a strong acid, so it immediately does what? Dissociates. This is a strong base, so it immediately dissociates. Okay? So what are my products that I get? My H positive is going to be looking for who? Which ion?
For the
The OH negative. H positive plus OH negative gives me what?
water.
Water. I'm going to get H2O. And so then Na is going to be with Cl. What do we know about NaCl and water?
Salt, water,
It is
salt.
soluble, which means in water it just stays what? Na positive plus Cl negative, right? So remember what we said? Strong, first of all, always wins. In this case, they're both strong, but we also say stronger what? Spectators. Look what happens. What did not change on either side of this equation? The Cl negative and the what? Na positive. So my net ionic equation is what? Do we see that?
What would be the equilibrium arrows?
Yeah, I guess you can do an equilibrium error. It wouldn't really matter. In this case, with a strong acid and a strong base, they're really not going to go back. Water can self-ionize, but remember, it only does like 2 of them per a billion. So, but either way, it'd be fine. If you did an equilibrium arrow or didn't, I wouldn't care. So don't stress about that one. Okay. So this is my net ionic equation. Please pay attention to these words. For every single time I have a strong acid with a strong base. So if you are so lucky, please let us be so lucky, okay? If you are so lucky that you get, okay, a strong acid and a strong base on the AP exam and they ask you for a net ionic equation, do not check up. H positive plus OH negative goes to H2O. They did put it on there one year. I'm just going to say a few extra pairs that put it in there again this year. So that's an easy one, right? We can do that.
So it's always gonna be that?
Always, if you have a strong acid and a strong base. This is always your net ionic equation. H positive plus OH negative gives me H2O.
Okay, cool.
Always. Okay? So, what you are going to be doing tomorrow, everybody got this because I'm about to erase it. Okay? What you are going to be doing tomorrow is we're going to have a beaker. We're going to fill it with some HCl. Then we're going to put some NaOH in a burette. And your burette just looks like a really tall graduated cylinder. Okay. And it's got a little valve on it where you can close it and open it, close it and open it.
It's so cool when it gets the one.
Okay. All right, and for the strong acid and the strong base, we're going to use bromothol blue. Okay, and I forget if it goes in yellow, it turns blue. If it goes in blue, it turns yellow. Or if it's colorless and turns blue. It's been a long time since I used bromothol blue. So we'll just know tomorrow what it's going to do. But it's going to change color. So as I add in the NaOH, my pH is going to do what? It's going to start going up, right? So my pH is going to start low because I'm starting off with all acid, no base, right? All about that base. About that base.
So are we trying to get it like neutral?
Huh?
We're trying to get it neutral? Like at 7?
So here's what you're doing. So you're going to see the pH slowly starts to move up, and then you're going to get a spike, and then it's going to slowly level off. Your equivalence point is right here. Okay, it's halfway between the spikes. So you'll see the top of the spike, the bottom of the spike. Your equivalence point is halfway between the spike. What should be the pH at my equivalence point for a strong acid and a strong base? 7, right? Because they neutralized each other. If you have done it correctly, your indicator should also change at this point, and when the indicator changes, we call it the endpoint. Now, if you didn't use the correct indicator, sometimes your endpoint and your equivalence point is not the same. Are you with me on this? So the indicator is like that bromothol blue. What changes color? Remember when we did it last year and it changed to that pink color? Okay, we're going to do that one again tomorrow too. But your indicator is what changes color. So you put a few drops of it in the solution, and once we reach a certain pH, it'll change colors.
So once it changes colors, it's at 7?
Yes. So what we are doing tomorrow is you're going to try to look, and when it starts changing color, because at first you're going to be adding 1 milliliter at a time, and we're just trucking along. And then all of a sudden you're gonna add 1 milliliter and it's gonna jump and you're gonna be like, whoa. And you're gonna see the color change and you're gonna be like, whoa. And then the color is gonna go away. And you're gonna be like, I promise, I saw that color and now it's no longer there. That's fine. That means you're not at the end point, but you are close. Okay? So that means instead of adding 1 milliliter at a time, I wanna do what?
Like a small.
I want to take it down to maybe like half or, just add a few drops at a time. What we're trying to look for is we're trying to get to the point where the color has barely changed, okay? I never managed to make that work in college, ever, okay? Like the second titration you do, you're looking for a faint pink. I mean, mine always went fuchsia, all right? Like it never got, y'all did do it last year, and a couple of you got faint pink last year.
I was suffering in class.
Fuchsia. Me, always. I even tried to help somebody last year and turn theirs fuchsia. I am terrible with titrations, apparently. Make friends with your GTAs in college. They liked me. They still gave me hundreds. So
if it like changes too dark, does that mean it's above 7?
yes. So if it goes too dark, then that means I've overshot my equivalence point. Okay. So that means I've gone past my equivalence point, so I know I didn't quite reach it. Okay.
If we do that, like, how do we get it?
It won't be a problem. Once you graph it, you'll still be able to see where your equivalence point should have been. So it won't be an issue. You're just trying to see if you can get your equivalence point in your input. And sometimes it works and sometimes it doesn't. And it's not a big deal if it doesn't because you've still got the data to graph. So you'll still be able to find this just by looking at your graph where it spiked. But it's just cool if you can make it work. Because used to, we didn't have, like what we'll have in here is a pH probe. And so we'll have a meter over here reading the pH for us. But used to, we didn't have those. Like they didn't even let us use those when I was in college. So what you had to do was you just had to go by the color. So that's why it was so important that you didn't overshoot it. I overshot it every time. Instead of pale pink, I got fuchsia. Literally fuchsia. It's pretty though. It was pretty. It wasn't right, but it was pretty. So you'll have a pH meter, so it's not a big deal. But it's just fun to try to make the color stay where it's supposed to be, okay? So let's look at this problem. Exercise 5 deals with the titration of a strong acid and a strong base, which is what you're going to do first. So I want to look at this one first, okay? So exercise 5 says, for the titration of 50 milliliters of 0.2 molar HNO3, I know HNO3 is a what? Strong acid. Okay. With 0.1 molar NaOH, I know that is a strong base. Calculate the pH of the solution and the following selected points of the titration. Okay. So I want you to think of this. Don't get scared when we do this. Think of it as a limiting reaction problem. Okay. Remember how we would do the mole to mole ratio? Okay. And you would get how many you started with. I'll show you. You'll get it. Don't let this scare you. Okay? So, first of all, it wants me to calculate the pH before we add any NaOH. So, no NaOH has been added. All I want is the pH of this HNO3 solution. Can I find it? Yes. pH is equal to what?
Log of H.
Opposite the log of
Hydrogen.
H positive, right? Do I know my concentration of hydrogen before I added any of the NaOH?
Yeah.
Yes. It's 0.2 because this is what kind of acid? Strong acid. So the concentration of the acid is my concentration of what? H positive. Thank you for remembering that. I appreciate it. Okay. Notice how many sig figs are in 50.0? 3. How many are in 0.200? 3. How many are in 0.100? 3. So how many decimal places do I need? 3.
I always forget if it's the leading zero or trailing.
Remember, put a box around the number you know is significant. I know 5 is significant. There's a decimal there. So all the zeros that occur to the right of the 5 count. If there were any to the left, they would not count. Left are losers. Right's not. Okay. Right are winners. Okay. Does that make sense? So, opposite of the log of 0.2 is what?
0.67. Or 6. No, it's not 7.
Okay, I got this. But I would be okay with 0.7002. Not really a big deal. So I would say this is pretty what? Acidic.
Yeah, it's very simple.
It's very acidic. Okay, remember, anything less than 7 is considered acidic, and that's getting real close to 0. Okay, so this is very acidic. So now B says, what if I add 10 milliliters of the NaOH? So I'm adding what? I'm adding base, right? So what should I expect my pH to do? Go up. I should be expecting it to go up, okay? But how do I know how it's affected my NaOH? Well, remember, here's my net ionic equation for a strong acid plus a strong base, right? Yes? You with me? So, how much of the H positive did I start with? Now remember, when we do limiting reactant problems, we don't keep it in molarity, we change it to what? Moles, okay? And if we remember, right, if molarity is equal to moles divided by volume, then the number of moles is equal to molarity times volume, right? Everybody agree with this? Yes? So back to this. I started with 50 milliliters of 0.2 molar nitric acid. So how much H positive did I start with? 50 times 0.2 is what?
No, I said that.
10. So I'm going to call this not 10 moles, because I kept that as what? Milliliters. So I'm going to call it millimoles, just because I love saying millimoles.
Explanation on the test one. She was justified.
Okay. So now I added 10 milliliters of 0.1 molar NaOH. Okay. So how many moles of OH negative did I add? So I would do what? 10 times 0.1, right? What's 10 times 0.1? 1. Do we see that? So I have 10 millimoles of H positive. I added 1 millimole of OH negative. Who is my limiting reactant here? The OH negative, right? Okay, so I'm going to use all of my OH negative. How much of my H positive am I going to use up? 1, right? One of this is going to react with one of this. So I'm going to have 9 millimoles of H positive left over. Do we agree with this? Do we see this? Okay. Now, can I calculate the concentration of my H positive that's left in the solution then? Yes. Now remember, pH is equal to opposite log of the concentration. Concentration is moles over what? Liters. So I've got 9 millimoles. What's my total volume that I have in the solution now? I started with how many milliliters? 50. I just added how many? 10. So 50 plus 10 would give me 60 milliliters. Does everybody see how millimoles over milliliters is the same thing as moles over liters? So I don't have to change them, do I? No. So I just do pH is equal to opposite the log of 9 divided by 60. And you should get 0.824. So did my pH go up? Yes. Is that what I expected?
Yes.
Yes. So now C says, what if I added 20 milliliters of NaOH? Okay. So instead of 10 milliliters in there, now I have 20 milliliters in there. So same thing. H positive, H negative, goes to H2O. How much H positive did I start with? 10 millimoles. We've already said that. How much OH do I have now? I would do 20 times what?
20 times
0.1, right? Because I'm working with my base. So 20 times 0.1 is 2. So I'm going to use all of my OH, right? And so how much of my H positive am I going to be left with? 8. Did we see that? So now can I find my pH? So now pH is equal to opposite the log of my concentration of my hydrogen, which is going to be 8 millimoles divided by, what's my total volume in this solution now? 70. Because 50 plus 20 is 70. And if you put this in your calculator, you should get 0.942. So my pH is still what?
Pretty acidic.
Still pretty acidic, and it's slowly going up. Am I going to slow down how much I'm adding at this point? No, because I haven't seen a jump, have I? So I'm not slowing down at all. I'm still going steady as the race. So now I've added 50 milliliters total of NaOH. Same thing again. I started with 10 millimoles of my H positive. How much of my OH negative do I have now? 5, right? Got 5 millimoles because 50 times 0.1 will give me 5. So who's still my limiting reactant? OH. So it's all going to be used, and I'm going to be left with 5 millimoles of my H positive. So now my pH is going to be equal to opposite log of 5 millimoles of my H positive divided by, what's my total volume now? 100. So if I put that in my calculator, that is what I got, 1.30. So now my pH has done what? It went up a little bit, okay? So now I might slow down a little bit if I was doing a titration, but I mean, I did add 30 more milliliters and I still didn't get a significant jump. So I'm still going. This is all in your procedure, so don't freak out. You don't have to like know this all on your own. All right, now E says I add 100 milliliters of NaOH. So I've got my H positive plus my H negative goes to H2O. Started with 10 millimoles of my H plus. Now I've got my OH negative. What's 100 times 0.1? 10 millimoles. Uh-oh, what do we see? My number of moles of my acid is the same as my base. So they have completely done what to each other? Canceled each other out. So my pH is equal to 7.000.
Could we just use this, like, what we just did right here? Couldn't we just do that, like, before we do the titration one? That way we know exactly how much we can have. Like, let's say you didn't have the year to do a titration.
Yeah, essentially. Okay. So when I have a strong acid and a strong base, and the number of moles are equal to one another, then my pH at that point is 7, and I know that I am at the equivalence point, because the equivalence point is when the number of moles of acid and the number of moles of base are the same. Everybody with me? Yes? And so then if, since we added 200 total, so I've got my H positive plus my OH negative goes to H2O. I started with 10 millimoles of H positive. Now I've got 200 milliliters of NaOH, so 200 times 0.1 would give me 20 millimoles. So now, who's my limiting reactant? H positive. So I've used up all of my H positive, and I have 10 millimoles in excess of my OH negative. There you go. So I would find the POH, which is equal to opposite the log of the concentration of, so I would do 10 millimoles over, what's my total volume now in this? 250. And if I did my POH, I would get 1.398. So now to get pH, I would just do what? 14 minus 1.398, and that gives me what? 12 plus. Does that make sense? Yes. Because at this point I have more hydroxide than H plus, so my pH should be above what? Above 7, because it should be basic.
This makes sense.
Does this make sense? You see this? We're not worried about this? So this is your first titration. Yes. Okay. Now, your second titration. Your second titration, we're going to titrate a weak acid with a strong base. Okay. Now remember, when we compare a weak with a strong, who always wins? Strong. Strong always wins. So this time, when I get to the equivalence point, should I expect my pH to be 7? No. I should expect my pH to be greater than 7 because I've got a strong base. So it's going to win the battle. So this time when I get a titration, okay, this equivalence point is not going to be at 7. It's going to be at some point that's greater than 7. Do we see that? Everybody understand that? Why it would be greater than 7? Yes? Okay. So this time when you do the titration, you're going to have acetic acid in your beaker. And you're still going to be adding our old handy-dandy NaOH. Okay? And this one's my favorite one because this is the one where you get to use the phenolphthalein as your indicator. So it is colorless, but then when it goes basic, it turns pink. Okay? And so if you do it correctly, you should get a very, 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 very light pink. Okay? If you overshoot it, you get fuchsia. But you still win because it's pretty to look at. So it's okay. So NaOH. So we're going to slowly add this in. What you're going to notice, and if you remember, I attempted this with pre-AP last year, but they redid the write-up this year, so it'll be more successful. And if you remember anything last year, we kept adding base, adding base, adding base, adding base, and our pH would never spike. It felt like it would take forever, and in our minds, this does not make sense, does it? This doesn't make sense. Why is it not spiking? Okay? Like, why is my pH not changing? Literally, we were adding so much NaOH and our pH literally was not changing. It wasn't changing at all. And we couldn't figure, the whole point of that last year was you weren't supposed to necessarily be able to figure it out. And you're going to see that tomorrow. You're going to be adding NaOH and your pH is not going to be changing. And you're going to say, but why? Why is it not changing? This is a weak acid with a strong base. So in my head, when I add that NaOH, what should happen? It should spike. This is a strong base we're talking about here. Why is it not spiking? Here is why it is not spiking. Now we can move to the beginning. So you can go to page 4. Why is it not hyping? Because what we have created is we have created a buffer solution. Okay? What is a buffer solution? Anytime I have a weak acid or a weak base, and it's salt. We're going to talk about that in a second. You need to know that the salt is actually the conjugate. Okay. I have created a buffer solution. What does a buffer do? A buffer resists a change in pH. So that makes sense. I'm adding NaOH. It's not changing. It's because I'm working with a weak acid. And anytime I have a weak acid or a weak base, what I have created is a buffer. Okay? Well, this doesn't make sense. You're saying, so how does it work? A buffer has both an acid, in this case, a base, and it also has its conjugate. What do I mean by that? If I have HC2, H3O2, right? Right. Now, some of this is just going to stay this. Do we all agree? Because this is a weak acid, so is it going to fully dissociate? No, it's not going to fully dissociate. But a little bit of it, not necessarily a lot bit of it, is going to dissociate into H positive plus C2, H3, O2 negative, right? Do we agree with this? You with me? Okay. So, this is my acid. When this hydrogen dissociates off, this ion then becomes my conjugate base. Do we see that? Yes?
Yes.
We see that? So, if I've got my conjugate base in solution, what's happening is I have an acid in here and I have a conjugate base in here. So every time I add something, I've got an acid to negate the base, and I've got a conjugate base to negate the acid. So what's happening is no matter what I add, my pH is not what? It's not changing. Does that make sense? Everybody see this? We got it? All right. So, what we'll have tomorrow is, so if a small amount, okay, of a strong acid or a strong base is added to a buffer, there's another component there that's willing to neutralize the invader. So if I quickly neutralize anything I add, is my pH going to change? No, it's not going to change. Okay. So what do we need to know so we can be able to solve these problems? We have to understand conjugate acids and bases, okay, which I feel like y'all have a pretty good hold on. Yes, ma'am. Okay, so we have to understand that if we have an acid, okay, then that negative ion is going to be the conjugate. Okay? Or in the case tomorrow, when I add this acetic acid plus this NaOH, one of my products is going to be this. Okay? This is the salt, right? Everybody recognize that as the salt? Okay? Na that is not only the salt, but it also releases the conjugate. What do I mean by that? Anything bonded to sodium is what in water? It dissociates. So that means this is going to dissociate into Na positive plus C2H3O2 negative. And this, we've already said, is our what? Conjugate base. Do we see that? So not only is this the salt, but it's also the conjugate base. You with me? Yes. So, what do we need to know? We also need to know that pH is equal to the opposite log of the concentration of H positive, which you already know. We have to know that Ka times Kb is equal to Kw, which you already know. And we need to know that this is equal to 1.0 times 10 to the negative 14th, which you already know.
Can we take this and narrow this one?
And we also know that anytime we have a titration with a weak acid or a weak base, that it is a buffer problem. So anytime I see that I have a weak acid or a weak base and I'm doing a titration problem, I need to realize that I have a buffer problem. So here's the one and only formula that you have to know in order to do buffer problems. And you need to memorize this because it will not be on your equation sheet. the concentration of H positive is equal to the Ka of the acid times the concentration of the acid divided by the concentration of the base. Seems easy enough, right? Okay. Why do I need the concentration of hydrogen? That's the only way I can know the what? pH. Okay. And most of these problems are going to be asking you to find pH. So let's go to exercise.
The order is out.
Huh? Sorry. I know, I'm jumping around today, but I wanted to do it in the order that you were doing your lab, not the order of the notes. It just made sense in my head. It may not make sense to you, it made sense in my head. Alright, so they tell us before we start that the Ka of formic acid is 1.8 times 10 to the negative 4. Okay? So this part of the problem we're going to say to do after we do the first part. So kind of put a circle around that and then pretend like the problem ends there. Okay. So it wants me to calculate the pH of 0.5 liters of a buffer solution composed of 0.5 molar formic acid and 0.7 molar sodium formate. Okay. So we're pretending like we have not added anything yet. All we're doing right now is calculating the pH before. Okay. So to calculate pH, I have to know the concentration of what?
Hydrogen.
H positive. I've got an equation for this now. I know that formic acid is a what?
Weak acid.
Weak acid. So therefore, I know that I can use my equation to get the concentration of hydrogen without even having to set up a rice table. Good news, right? Right. So this is equal to Ka times the concentration of the acid divided by the concentration of the base. Do I know the Ka? Yes. It's 1.8 times 10 to the negative 4. Do I know the concentration of the acid? Yes. What is the concentration of the acid? 0.50 molar. What is the concentration of the base? 0.70 molar. Can I solve for the concentration of hydrogen? Yes. I put it all in my calculator, and I get that the concentration of hydrogen is equal to 1.29 times 10 to the negative 4. Now that I have the concentration of hydrogen, can I find my pH?
Yeah.
Yes. And say pH is equal to opposite the log of 1.29 times 10 to the negative 4. So my pH is equal to 3.89.
Why? No, I'm just kidding.
We see that? We're good with that. Now, it wants to know my pH after I add 10 milliliters of 1 molar HCl. Okay? Here's what you need to know. When I am working a buffer problem, and what is my clue that I am working a buffer problem?
Do you have a weak acid and strong?
I have a weak acid or a
Weak base.
weak base. Either one of them. It doesn't matter. Okay? When I see this, I automatically know when we see the word after means we need to go to moles. We don't need to stay in molarity. We need to stay with moles. Okay? Now, we are adding HCl. HCl is a what?
Strong acid.
It is a strong acid. So, we go up here, all right, and we say, if acid is added to the buffer, we add acid to the numerator, and we subtract the same quantity from the base. Why are we subtracting from the base? Because if I added acid, what did it react with? The base. So the base was self-sacrificing to trying to do what?
Neutralized.
Neutralize the acid. So I added acid, and in the process, that meant I took away what? Base. Now, if I would have added base, then I would have done the exact opposite. I would have added to the base and taken away from the what? Acid. Do we understand that? All right. Now, remember, okay, when we go to the after, we add or subtract in moles, not molarity. So we have to remember, and we just used this earlier, that moles is equal to molarity times volume. If we end up with an equal concentration or an equal number of moles of the acid or base, and this happens at the half equivalence point for a buffer titration, okay, that means the ratio of acid to base is equal to 1. So let's look at this. If this becomes 1, then my concentration of hydrogen is just equal to what? My Ka value, right? Do we see that? So then if I had to find pH, I just take the opposite log of K, so we call that pKa. Do you see that? Because pH is opposite the log of what? Hydrogen. So pKa would be opposite the log of Ka. Does everybody see that? So my concentration of hydrogen is equal to my Ka if my acid-base ratio is what? 1. Do we see that? I feel like I've lost some of you, but it's okay. So let's go to my after. We're going to moles. So now my concentration of hydrogen is still equal to my Ka, which is still 1.8 times 10 to the negative 4. I didn't change that. My acid over my base. Okay. Now remember, when we go to after, we've got to go to moles. So I've got to change my molarity to moles. How do I change molarity to moles? Moles is just equal to what? Molarity times the volume. Okay. So what did I start with? I started with 0.5 liters of my formic acid. So to get my original moles of acid, I just do 0.5 times 0.5 and I get what? 0.25 moles, right? So how many moles of the base did I originally start with? I started with 0.7 molar, still with 0.5, so 0.5 times 0.7 is 0.35. Now, I added what? Acid, right? So how much acid did I add? This is in 10 milliliters. Since I've already worked this calculation in liters, I need to change this one to what? Liters. So I go back 3 decimal places. 1, 2, 3, and change that to 0.01. My molarity is 1, so volume times molarity gives me moles. So what's 0.01 times 1? 0.01. So I'm going to add it to my acid. Why am I adding to my acid? Because it's an acid. I added acid in. And I'm going to subtract that same amount from my base. Do we see that? What's 0.25 plus 0.01? Please don't put that in your calculator. What is 0.25 plus 0.01? Thank you. So this is 0.26. What's 0.35 minus 0.01? 0.34. And now we can put it in our calculator. Can I find the concentration of hydrogen now? Yes. I can. I got 1.38 times 10 to the 4th. Or negative 4th in here. So then my pH is equal to opposite the log of 1.38 times 10 to the negative 4th. So therefore my pH is equal to 3.86. Notice I added an acid, so my pH did go down, but did my pH go down a lot? No. Okay. Should I have expected it to go down a lot?
No.
No. Because this is what kind of solution? Buffer. What do buffers do? They resist a change in pH. How do I know I'm working with a buffer solution? If I see a weak acid or a weak base. Make sure that you don't forget to get that pre-lab done tonight.
They do the lab for this. They do the lab for this.
Yes. So, I will see y'all tomorrow.